Hello everyone. Let us discuss about erythro and trio, PS, cis, trans. What are these? These terms may sound weird, but they are important for competitive exam. Erythro and trio, they are stereochemical prefixes. Now, it is used to represent a molecule stereochemically, particularly in carbohydrates. Like in erythro, if we say, it describes the stereochemistry of molecules where the two adjacent chiral centers are there, often in Fischer projections. In Fischer projection, we get two adjacent chiral centers. For two adjacent chiral centers, we have representations like erythro and trio. If similar groups are on the same side in Fischer projection, then the compound is erythro. Now here one example I have written, that in tartaric acid derivative or 2,3-dihalo compound, we can see the relative positions of this halo and we can judge, or we can just see over here like erythro I have made like R1 on the left hand side, R2 R3 at the top and the bottom, and R4 on the right hand side. So we can see R1 on same side, R4 on same side. But in trio, it is just the opposite. It's just like the trans one. R1 in opposite side, R4 in opposite side. But there are two chiral centers which is adjacent to each other. Next, you can see that what I said is trio, where it is the opposite of erythro, and the similar groups are on opposite sides in the Fischer projection. Now P and M, P stands for plus, M stands for minus, but at times it is written as PS also. Now this is known as helical chirality in molecules, and these molecules are termed as helicenes. Like we know, helicenes or substituted biphenyl. So P stands for plus or right-handed helix or clockwise twist of the helix. M stands for minus or left-handed helix or anti-clockwise twist of the helix. Now what is this helical chirality? It's a very new term. Helical chirality is a type of chirality where a molecule becomes chiral because its atoms are arranged in a spiral or helical manner, in a helical shape, rather than having a chiral center. Because previously we have seen that in the CBSE curriculum, we have seen that chirality exists if the carbon atom is chiral and it is present in the molecule. But here we are seeing that if the structure of the molecule is a helix, then it shows chirality. A molecule will show helical chirality when it twists like a helix or spiral, and the two possible twists are non-superimposable mirror images. Now these two possible twists are one P helix and the other is M helix. Now, if you think of a spiral staircase, you might have seen spiral staircases. If it turns clockwise upward, the spiral staircase, if it turns clockwise upwards, then it is an example of a P helix, and if it turns anti-clockwise upwards, then it is an example of M helix. So clockwise turn is P helix, anti-clockwise turn is M helix. So let us try to visualize it. This is just for visualization. Here we are seeing P and here we are seeing M. We can see how it is just the opposite turns. And now stability and switching. Switching means converting from one form to other. Solvent polarity and temperature, these two factors can actually cause a flip in the two forms, P form and M form. And this is known as helix inversion, because an inversion of the stereochemistry of the molecule occurs from a P form to the M form, or M form to the P form, without fully unfolding the molecule. The helix gets inverted, but you know that the molecule totally doesn't get unfolded. This type of interaction is non-hydrogen bonded interaction. See, in CBSE Till class 12 CBSE curriculum, you had seen disulfide bonds, van der Waals interaction, you had seen hydrogen bonding. But here this is some type of interaction which is a non-hydrogen bonding based interaction due to the effect of the solvent but not hydrogen bonding. So this occurs, of course, between a pure p helix and pure m helix. Examples of molecules showing helical chirality. Helicene is one such, where a series of fused benzene rings that naturally twist into a helix because of the structure. If there are series of benzene rings, where does it happen? It occurs in pharmacokinetics, medicines, where the compositions are such that the structure of the compounds that are present are such that there are n number of benzene rings fused to each other. Alene system, that or substituted alene system, that is, you are having adjacent C double bonded C systems attached to it. Now, or coordination complexes and say biopolymers. Now, deoxyribonucleic acid, DNA itself is a right-handed helix. This we know. Next, cis and trans. We all know what is cis-trans isomerism. We have seen in the CBSE curriculum that it is used for the geometrical isomerism, where the groups, if they are arranged on the same side of the double bond, they are what? They are cis, and if they are arranged in the opposite side, they are trans. Examples can be shown by but2-ene or maybe any chloro, bromo, any substituent given to it. In but2-ene, we can consider the CH3 groups on the same side to be cis, and if they are on the opposite side, to be trans. So that's all for a nutshell discussion of erythro, trio, PS and cis trans.